After a detailed analysis of four types of interactions, now today we are going to discuss a very important concept of physics. This is not actually the concept of elementary particle only, but you can say that this is the concept of physics because this concept is used in almost all branches of physics. In fact, you have studied different conservation laws or conservation principles in different branches of physics. For example, definitely you have studied conservation of momentum, linear momentum, conservation of angular momentum, conservation of energy, and so on. But you must remember these conservation principles are always related to some symmetry or invariance. So this lecture is just related to the conservation laws and symmetry in physics. But we will mainly focus on those laws which are studied in the study of elementary particles because our chapter is elementary particles. So main thrust will be on the conservation principles which are studied in elementary particles. But as I have told you that this is concerned not only with the conservation principle which is studied in elementary particles but all the conservation principle or laws in all branches of physics. Actually, I have divided this lecture in two parts. This first part of lecture will be just an introduction for the conservation laws and symmetry. In fact, you have seen that in course of the dynamical development of physical system, though many of the observables change their values, but there may be one or more physical observables which do not change with time. It means there are observables which remains constant during the study of during the physical change of any system. In fact, the observables which do not change with time, those are actually called constants of motion. In the study of classical mechanics, we have definitely studied different constants of motion. And you should note that when you say that there are some observables which are constants of motion, definitely with those constants of motion, a principle of conservation of the quantity is associated. For example, if you are talking about a free particle, it means a particle which is not acted upon by any external force or the resultant external force on the particle is zero, then you have definitely studied that the linear momentum of the particle remains conserved, and so the linear momentum of the particle of a free particle is called a constant of motion. But when that particle is moving under the influence of a spherically symmetric field, for example in a gravitational field or in an electric field, then you know that the linear momentum varies with time. But even in that condition, the angular momentum and the energy of the particle remain constant. And so, for a particle moving in a central force field, the angular momentum remains constant, energy remains constant, and so angular momentum and energy are called constant of motion for a particle moving in under a central force. But in that condition, the linear momentum does not remain conserved, that changes, and so that is not a constant of motion. In fact, this constancy of motion, that is when you say that a particular quantity is a constant of motion, Definitely that conservation law is related to some symmetry operation, or you can say some invariance principle. Okay. In fact, since the beginning of physics, symmetry consideration have provided an extremely powerful and useful tool in our effort to understand the nature. Gradually, they have become the backbone of our theoretical formulation of physical laws. You know, it is well known that the principle of symmetry play an important role in physics. Furthermore, if a symmetry or invariance exists, then the conservation of corresponding quantity is definitely followed. So I have mentioned here some of the invariance or symmetry principle and the corresponding conservation law. You can see here I have mentioned that if the space time is symmetric, or you consider that the invariance of space time, the invariance of space time actually leads the conservation of linear momentum and energy. Okay. When you say that the space time symmetry, what does it actually mean? Actually, the space time symmetry refer to the symmetries associated with geometrical operations like displacement, rotation, and inversion. That is reflection at the origin in space and time. For example, the assumption that the space is homogeneous. If you consider that our space is homogeneous, that requires that Hamiltonian as well as the probabilities associated with the physical system will be invariant under displacement or translation in space. Okay? And you will see later on that such a translation invariance implies that the linear momentum of the system remains conserved. You will see later on. And you have definitely studied this in your course on classical mechanics. If you have not studied, you can go through my video on this conservation laws and symmetry principle in my playlist of classical mechanics. You can see. And similarly, the invariance of rotation leads to the principle of conservation of angular momentum. Okay? As I have told you that the invariance under rotation has its origin in the isotropy of a space. It means that a space has same properties in all directions. That is called isotropy of a space. And this isotropy of a space has the importance of geometrical symmetries associated with space and time for and that leads to the principle of conservation of angular momentum. Okay. And similarly, when you talk about the symmetry under reflection, that is the origin is just reflected, r is changed into minus r, then this symmetry under reflection, you will see later on that this leads to the conservation of parity of the system. Okay. In the similar manner, we will also study later on that symmetry under exchange of particle and antiparticle leads to the principle of conservation of charge conjugation. Okay. And we will also see that if there is an approximate symmetry of up and down quarks, then this leads to the approximate conservation principle of isospin. These are some of the important examples which I have cited here to clarify your concept that every conservation principle is associated with some symmetry or invariance. Okay. I have mentioned here some of the examples. But in our course of elementary particle, after completion of these two lectures on symmetry and conservation laws, we will study actually in detail the different conservation principles. Okay, some of the important conservation principles you have studied in your course on classical mechanics, like conservation of linear momentum, conservation of energy, conservation of angular momentum. And all those conservation principles which are related to the study of elementary particle, we will study in this series of videos. Okay. In fact, when you think about symmetry, what does actually it means? In fact, thinking about what symmetry means in such cases which I have mentioned just now, we realize that it refers a situation in which there exists several different states that however are basically equivalent to each other with respect to the laws of physics. Actually, symmetries imply that laws of physics are invariant to the symmetry operation in which we state uh, that one state is just equivalent to another. It means whenever a symmetry operation will be performed on a system, the new state of the system will be obtained after the symmetry operation, but that new state will be just equivalent to the previous state. So the physical quantity which is related to that symmetry operation does not change, that remains constant, and that leads to a conservation principle. Okay. In fact, if you consider that there are two states, these two states are actually denoted by the Dirac notation. Let us consider that if you consider that the first state of our system is, let us say, Kate A, and after the symmetry operation this state is changed to, let us say, Kate A hat. In fact, these two states, that is Kate A and Kate A hat, Kate A prime, these two states are actually equivalent to one another, and these are called actually the equivalent states. Okay, and so in fact the quantity which will be related to these two states, that will not change and that will remain conserved. Okay. So you can say that if physical laws possesses symmetry, existence of an arbitrary state, let us say Kate A, would imply that any equivalent state formed by symmetry operation, which I have mentioned here by the state Kate A hat, must be also possible. As I have told you that when we will do a symmetry operation on our system, the state of the system which was previously Kate A now becomes Kate A prime. But these two states are equivalent to one another. Okay. So the physical laws will not change in this new state of the system. You can clarify this idea. What actually I want to convince you. Let us clarify this by a particular example. Let us consider that there is an electron, and you know the electron has a spin angular momentum, and let us say that electron is placed in an external magnetic field which is directed in z direction, and a unit vector in z direction is z hat. So you can say that the external magnetic field is applied to the electron in z direction. Okay, and the spin angular momentum of this electron is, let us say, s. Then you know that the component of this s along this direction of magnetic field or z direction, which is denoted by sz, this is given by ms times h bar. You know it. And you know this ms will be actually equal to half plus half, and this will be plus half h bar. Okay. This ms may be also minus half. Now, if we rotate the direction of this field, now consider I am showing here in another figure that initially the field was directed in this z hat direction. Now let us consider that the field is rotated in this z prime hat direction. In fact, in that condition, the two states of the electron will be just a characteristic of the electron, and no property of the electron will get changed. Okay, so you can say that the characteristic of our electron do not depend on the direction. Okay, so here the electron has two states. In first state, the magnetic field is applied in z hat direction. In the second state, the magnetic field has been applied in z prime hat direction, which is actually rotated by, let us say, some angle theta to the previous direction. So actually these are two different states of our electron, but a physical law related to that electron will remain same in both of these states. So we simply say that any characteristic of this electron will remain same, and so that does not depend on the direction of the applied magnetic field. Okay. Now, in fact, in physics, there are four important groups of symmetry. We will study these groups of symmetry later on in very detail, but as I have told you that this is our introductory lecture on symmetry and conservation laws. So till now you have seen that any conservation law is associated with some symmetry or some invariance. Okay, but what type of symmetry exists in the study of physics? So as I have told you, there are four main groups of symmetry or invariance. The first one is called actually continuous space symmetries. Continuous space symmetries. And when you say continuous space symmetries, actually this continuous space symmetries are associated with displacement in space and time and rotation in space. Okay. And so you can say that the example of continuous space symmetry is translation, rotation, acceleration, etc. In fact, this continuous space symmetry is actually of universal validity. It means this symmetry holds good for all the known interactions. You know that there are four interactions, that is gravitational interaction, electromagnetic interaction, weak interaction, and strong interaction. This continuous space-time symmetry holds good in all these four interactions. Okay. It means this symmetry is never broken. Okay. Now, the another important group of symmetry is called permutation symmetry. Permutation symmetry. And the important example of this permutation symmetry is the well-known Bose-Einstein statistics and the Fermi-Dirac statistics. In fact, Bose-Einstein statistics and Fermi-Dirac statistics are the example of permutation symmetry. And you should remember that this permutation symmetry is also of universal validity. It means this symmetry is never broken. It holds in all types of interactions. Okay. Now, apart from the continuous space-time symmetry, there is also discrete symmetries. Okay, discrete symmetry, and this discrete symmetry, you can say that example of this discrete symmetry are space inversion, time reversal, particle anti-particle conjugation. These are the important examples of discrete symmetries. In fact, this discrete symmetries are not of universal validity. You will see in some interaction it is broken. It means this symmetry does not hold in some of the interactions. For example, when you consider that there is a space inversion, if you think about the space inversion in case of weak interaction, you will see that the space inversion in weak interaction is not actually valid. For example, you have definitely you have studied in the previous lecture the process of beta decay, and you have seen that parity violation takes place in beta decay. It means parity does not remain conserved in beta decay, and you know that beta decay is just an example of weak interaction. And when you talk about parity, the parity in case of parity, actually there is an inversion of a space. Okay, and when the space inversion is taken place, and you know that parity does not remain conserved, it means this space inversion symmetry breaks in case of weak interaction. So I have told you that the space inversion invariance is not valid in case of weak interaction. Similarly, the time reversal inversion also seems to be violated in certain reactions. For example, the decay of, in case of decay of neutral kaons, you will see later on that this time reversal symmetry breaks. So symmetry may be of universal validity or it may not be of universal validity. So this discrete symmetry is not of universal validity, as I have told you. In some interaction it breaks. Okay. Now the fourth one is actually the internal symmetry. All the above three symmetries was external symmetry, but there are some internal symmetries which is also called unitary symmetries. Now these internal symmetries are actually of four types. You should remember that unitary or internal symmetry is of four types. The first one is called U1 symmetries. Okay. Actually, this U1 symmetries are related to the conservation of electric charge, baryon number, and lepton number. These are some important examples where U1 symmetries actually exist. Okay, and this U1 symmetry is also of universal validity. You should note this, that this U1 symmetry never breaks. It holds in all types of interactions. Okay. The next type of unitary symmetry is SU2 isospin symmetry, and this is not of universal validity. We will see later on. I am just giving you just an information about the different type of symmetry here, but in the forthcoming lecture we will discuss in very detail these type of symmetries. We will study this SU2 symmetry in very detail in the forthcoming lecture. The third one of this unitary symmetry is SU3 color symmetry. Color, you know, this is just a quantum number in case of quark. Okay, and the fourth one is called SUN flavor symmetry. Flavor is also a quantum number. When you study the quark, then these flavor, color, charm, these are actually called quantum numbers. And as I have told you just now, that this symmetry in some cases breaks, and there are some symmetry which holds in all types of interactions. So all those facts which I have just mentioned, I have mentioned here in this remarks. So you should note these things. Already I have explained this, and I am just giving a reading what I have just told you. As I have told you that among these, the first two groups, when you say first two groups, it means what? It means the continuous space-time symmetry and the permutation symmetry. Okay? These two groups. And together with some of U1 symmetries and perhaps the SU3 color symmetry in the last group are believed to be exact. When you say it is believed to be exact, it means it holds, it is of universal validity, it holds almost in all four interactions. Okay? And remaining group of symmetries I have mentioned here, that all the rest seems to be broken. It means the remaining group of symmetry is not of exact nature. They are not valid always in all types of interactions. But in some interactions, that symmetry does not hold. As I have told you that the that the space inversion symmetry is not valid in case of weak interaction. Okay, as I have told you. So what does it mean? It means continuous symmetry, permutation symmetry, and some of the U1 symmetry and SU3 color symmetry have universal validity. That is, they hold good for all known interactions. This will be just okay. The page has been turned, but don't worry, this is just okay. See here, I have mentioned all these things just now, but I have written it so that you can write these things in your notebook. So you can see that the continuous symmetry, permutation symmetry, some of the U1 symmetry and SU3 color symmetry have universal validity. That is, they hold good for all known interactions. But a space inversion invariance is not valid in case of weak interaction. Time reversal invariance also seems to be violated in certain reactions. Just for example, in the decay of neutral kaons, this time reversal symmetry does not hold. Actually, this neutral kaon cannot be transformed directly into the anti-neutral kaon, but it in case of weak interaction, first of all, it is transformed into pi 0 plus pi 0 or pi plus plus pi minus. This is actually the decay process of a neutral kaon, and we will see later on in the forthcoming lectures that this decay process actually, in this decay process, actually the time reversal invariance is violated. It does not hold. So the gist of this introduction is simply that every conservation principle is associated with some invariance principle or symmetry principle. So when there will be any type of symmetry, that symmetry will lead to a particular conservation principle. But in the next part of this lecture on symmetry principle and the conservation laws, we will actually explain theoretically by mathematical calculation the concept of symmetry and conservation laws in very detail. So definitely you should watch the forthcoming lecture in continuation of this first lecture. This was just a lecture to introduce you only to know that every conservation principle is associated with some of the symmetry. Okay, and what are different types of symmetry? I have just given an information, not any detail, but in forthcoming lecture we will study these different types of groups of symmetry in very detail. Okay, so wait for the next lecture, and I hope you will join, you will watch the next lecture on this symmetry principle and the conservation laws.